So finally, we're going to embark on the journey of entanglement and entanglement states and so on. Just entangle. So I want to clarify a couple of things before we go on. So everything I talked about in the two-level QM lecture referred to single particle quantum physics. Okay, so either a particle was in a state 0, or it was in a state of 1, or more generally, it was in a state that's a superposition of the two. Okay, so a lot of what I talked about in the previous videos is about how to identify the evolution of these quantum states and express that in terms of its eigenstates. Okay, so when you only have a single particle system, there's no notion of entanglement. Okay. So it's like if you are the only person living on Earth, there's no notion of a friendship, there's no notion of a hatred or a conflict, because there's no one else to get into a conflict with, no one else to love. And so the entanglement is about the state of at least two particles, number of particles being at least equal or greater than 2. And as such, this is just a generic many-body feature. Okay, so any quantum state consisting of more than one particle is called a many-body system. And for any sort of many-body physics or many-body quantum states, there is this issue of entanglement. So as such, it has nothing to do with the recently popular quantum information or quantum computer sciences. The idea of entanglement was born in the 1930s. So to give you a brief historical context, it was born conspicuously through the publication of a paper by Einstein, Podolsky, and Rosen. Einstein was, of course, a famous scholar who had moved to Princeton and settled down at the Institute of Advanced Study. And there he met these two young students, I think, Podolsky and Rosen. And the three of them together wrote this famous paper talking about the puzzling aspects of quantum mechanics. And what they talked about is basically the question of what happens if there are two particles. What if there were two particles and their wave functions were in some sort of weird state, which we now know, which we can now identify as the entangled state? And then about a year later, Schrödinger tried to clarify this issue raised by the EPR paradox, EPR paper, and he came up with the more solid foundation for the entanglement. And it is said that he even came up with the word entanglement in one of his papers published around 1931. So the idea of entanglement has been around ever since the early days of quantum mechanics, and and the reason why we don't get to talk too much about it in at least undergraduate curriculum of quantum physics is that the undergraduate quantum is mostly about single particle physics. Okay, I mean, if you think about the hydrogen atom problem, it's about a single electron moving around in some potential field, and the potential well problem that you solve so diligently is also about the motion of one quantum particle subject to some sort of a potential landscape. Okay, so basically almost everything you learn through the undergraduate quantum curriculum is about the single particle case. And perhaps that's why we don't normally get to talk about entanglement at all in such a curriculum. But I think it's time to change that perspective, since more and more of what physicists are interested in and what physicists think as important future problem have to do with the quantum information and quantum computers, where the entanglement is just an essential ingredient. Okay, quantum information, quantum computer sciences cannot exist without the well-entangled state. Okay, so why this is why this is the case will hopefully become more clear toward the later parts of my video. But let me just stop with such a statement for now, and maybe clarify the this idea with some explicit examples. Okay, so let's say I have a two-particle system, n equals 2, and each particle is in a two-level system. Okay, so a particle, a first particle can be in either psi1 or psi2. These are the two basis states. And let me also add this extra subscript to show that this is a state for the first particle. But there's a second particle that one has to place into some quantum state. So that's also going to be in one of these two possible basis states, psi1 and psi2. But this psi1 is different from this psi1 in the sense that it occupies the other quantum state. To be more precise, it occupies the other Hilbert space. So let me add a subscript 2 to indicate that this is the quantum state made available for the second particle. However, the wave function is for the entire many-body system. Here, many-body means two-particle system, of course. And so this many-body wave function, which I write as a psi, will be either the first particle occupying this state and the second particle occupying this state, or maybe the connection is like this, or maybe the first particle occupies the psi 2 and the second particle occupies psi 1. And finally, there's this possibility of both particles occupying the psi 2 state. So the possibility is that there are 4 possible states: psi 1, psi 1, 1, and psi 1, psi 2, and psi 2, psi 1, and psi 2, psi 2 for particles 1 and 2. And of course, this being a quantum mechanical state, you can introduce arbitrary mixing coefficients, which is some complex number A11, A12, A21, and A22. Okay, so symbolically, you can write down a arbitrary two-particle state as a sum, Aij, psi I, 1. And sometimes people put this product with a circle around it to indicate that this is either a direct product or a tensor product. People use both terms. And this is the most general way of representing an arbitrary two-particle state, each particle occupying some sort of two-level quantum system. Okay, so how does all these mathematics of the two-level system carry over to the two-particle wave function? Well, first of all, there is the orthogonality stuff that one has to take care of. So the orthogonality between, let's say, psi I prime for the first particle and psi j prime for the second particle, overlapping with the psi I for the first particle and psi j for the second particle, is equal to the overlap of the basis functions for the individual particles. So it breaks down as this product multiply this is just ordinary multiplication, not a tensor product. Okay, so this is the rule, and since each overlap boils down to a delta function, we have this overall delta function for normalization, which is of course quite sensible result. Okay, so first of all, let's consider a simple scheme for making a product. How to make a two-particle state out of one-particle state. So what I mean is that the first particle, psi 1, is in some sort of quantum state, bi psi I1, as a linear combination of the basis states within its own Hilbert space. And the second particle is also in some linear combination of states with, of course, different coefficients, ci, psi I, and make sure to put the subscript because this is a Hilbert space for the second particle. And then the overall wave function is given by this direct product of the two wave functions. So combining all these expressions into a product, we'll find such a thing, psi I1 multiplying psi J2. Okay. Now, let's compare this to the most general expression for the many-body state, psi I1 cross psi J2. Okay, of course, in order for these two expressions to match, we must have Aij equals Bi times Cj. So you can see that this coefficient sort of factorizes into product of coefficients coming from each Hilbert space. Okay, so when this sort of factorization happens, then we say that this many-body state, this many-body state was, in fact, a product state. Okay, and the meaning of the word is pretty evident from the fact that this many-body state is really just built out of these product of the individual quantum state. And such a product state, by definition, is unentangled. Okay? So a product state is an unentangled state. And for the product states, these coefficients will satisfy this sort of factorization scheme. Okay, so then it's easy to guess that when this factorization does not work, then such a quantum state will be called entangled state. Okay. So this is a simple way to tell whether a given many-body state is entangled or unentangled. But it's not always easy to tell, right? Because if you start with these individual quantum state and then you simply take the product like this, or for example, you can take the product of 3 different particles like that, then the many-body wave function coefficients Dijk is given by the product of the coefficients from each state, Ai, Bj, Ck, where Ai is the coefficients coming from the first particle, Bi is the coefficient coming from the second particle, Ci is coming from the third particle. So you can almost easily anticipate that such a factorization should take place. However, if we are just given some sort of many-body state in this form, and ask is Aij factorizable or not? that's actually a much harder question, right? So let me illustrate the difficulty with an explicit example. Let's say I give you this particular example of a two-particle state. Okay, so 0, 0 means that I put the first particle in the quantum state 0 and the second particle also in the quantum state 0. And 1, 1 means I put each particle in the quantum state 1. Okay, so is this a product state or not? Is this entangled or unentangled? Okay, just by looking at these expressions, it's not that obvious whether it's entangled or not. So let me try to come up with a proof to see whether this is entangled or not. And the proof goes like this. Assume that this is indeed factorizable. Then factorizability would imply that this wave function over here can be rewritten as a product of these one particle wave functions. Okay, so this is a wave function for the first particle, and this is a wave function for the second particle, and the two-particle wave function is the product. Okay, now in order for this expression to match that expression, we better have A times C equal to 1 and B times D equal to 1, but also A times D equal to 0 and B times C equal to 0. But it's pretty clear that these conditions cannot be satisfied because A times D equal to 0 means that at least one of these coefficients has to be 0. Let's say A is 0. Then it will be in immediate contradiction with this other condition, namely A times C equal to 1. Okay, so we arrive immediately at the conclusion that this state is not factorizable. And if it's not factorizable, then the state must be entangled, because that's what the entanglement is all about. Okay, so you can pretty much see that there are a lot more entangled states than unentangled state. Unentangled state. Okay. But then how can we tell? How can we tell if let's say if I have some sort of n particle state, right? A, I1, I2, In. So there's a huge set of indices, and the basis states are I1, I2, In. And let's say we are talking about the two-level system for each particle. Then all of these individual indices can be either 0 or 1. So there's a total of 2 to the n numbers, or 2 to the n coefficients. Which fix the wave function. And let's say n is 10, so I throw in your face some wave function with 1024, which is 2 to the 10 coefficients. Okay, and then I demand that you tell me, or I demand to know, if this wave function is entangled. Or if not entangled, then it's got to be a product state. So which one is it? Okay, so I hope it's pretty clear that unless there's a systematic mathematical way to sort through this sort of question, it's going to be pretty impossible to figure out just on the basis of these bunch of numbers to tell whether a given quantum state is entangled or not. And so that's where the well-known mathematical knowledge of something called the singular value decomposition, also known as the Schmidt's decomposition, comes in. And so this is a kind of knowledge of linear algebra that we don't really get too much exposure to. We did not learn. By this, I mean singular value decomposition. We did not learn this in quantum mechanics. We did not learn this in linear algebra. In fact, we did not learn it from anywhere. Because we did not have to. And the reason we did not have to was because we were almost exclusively concerned with the one particle physics. However, now there's a growing importance to know and be very good at these singular value decomposition techniques. Thanks to the growth of the importance of quantum information science, quantum computation, and machine learning. Because so much of the machine learning principle relies on manipulating the data through the singular value decomposition. So given that these are some of the most exciting growth areas in engineering and physical sciences, it's well worthwhile to spend your time and resources to learn about singular value decomposition. So I will devote my next video to the theory of the singular value decomposition.